Okay, the lighting here is just not perfect. No matter which way I turn it, I get the glare in the eye. So just focus on the lessons and not on me. The second chapter of this book by David Archer on the global carbon cycle primer is called the stable geologic carbon cycle. So we looked at carbon cycle through Earth history, and then we argued that it's a moody beast with a stabilizing negative feedback at weathering timescales, like a CO2 thermostat, which is working on a 100,000 year timescale, but on the glacial deglacial timescales, especially when we looked at the Vostok ice core data, we see that it's part of the positive feedback along with the glaciation, deglaciation, temperature change, and so on. Here on geologic timescales, the carbon cycle acts to stabilize the climate and oxygen concentration as well of the Earth in mysterious and wondrous ways. We will see how many components are involved in the carbon cycle, and it still remains a stabilizing, stable carbon cycle. So this is just a way of saying it again. Carbon cycle is Earth's thermostat. So we'll come back to global warming eventually, about emissions of greenhouse gases by human beings and the rate of change. But we have to look at the geologic past to understand the various aspects of how greenhouse gases, mainly CO2 and the carbon cycle, interact with the climate sensitivity over time. So we have to go through these carbon cycle aspects, whether it's positive feedbacks, negative feedback, whether it's stable. But stability here also is kind of interpreted in a very long time scale, where we went from the sun being 30% less luminous, less energy coming in, to where we are now, and the temperature, global mean temperature of the Earth, has remained fairly steady on those timescales. Of course, it's been very warm in the past, the Cretaceous hothouse and the ice house along the way, and so on. So we'll look at snowball Earth in the next chapter, etc. So we have to keep everything in perspective, the timescales and the timescale at which we are perturbing the carbon cycle now. So just keep that in mind, okay? So here, if the Earth warms, then we have more CO2 typically in the air, means more greenhouse effect, and that's going to create warmer Earth, but that's going to create more evaporation and more precipitation. There is a exponential relation between air temperature and air humidity. So as you increase temperature by 1 degree, you're going to increase humidity by 7%. And on a global average, this leads to more precipitation, and more CO2 is dissolved in the rainwater, and that's going to increase the weathering rates. So less CO2 in the air means less greenhouse effect. So you're going to cool the Earth, but then you're going to have reduced evaporation, reduced precipitation, and less CO2 dissolving in rainwater, and increase the CO2 in the atmosphere. Of course, there's weathering and carbon drawdown involved as well, because as Earth warms, warmer temperatures favor faster weathering rates, which also tends to draw down the carbon dioxide, which is related to the more CO2 dissolved in rainwater. So this is the kind of simple way of looking at it. There are other hypothetical stabilizing forces in the system. James Lovelock in the 70s, and then Lynn Margulis proposed the idea of Gaia hypothesis, which says that there is a homeostasis between living things and their environment. This is debated. This is more of a philosophical point of view, but the idea is explained very nicely with what is called the daisy world. Very simple mathematical model where you take Earth with a soil that has a certain albedo or a certain absorptivity of solar radiation, and then you have daisies, which are, let's say, flowers with bright color and then darker color. So if you have more daisies, you're going to increase the albedo of the Earth and cool the temperatures, and you have more dark daisies, then you're going to absorb more of the sunlight and increase the temperature. So without having any brain, if the growth rates of these daisies of different colors are differently sensitive to the global temperature, then you can imagine that if there is an orbital change, for example, as we looked at the glacial deglacial cycles, remember the radiation level at 65 north as a main driver of glaciation and deglaciation in terms of end of the summer snowmelt and survival through the winter and so on. Here, warmer temperature will, for example, favor lighter daisies, and more lighter daisies will grow and the darker daisies will not do well in a warmer temperature. So soon enough you have lots of white daisies and you have increased the albedo, and that's going to reflect more sunlight and start cooling the temperature. So then the darker daisies are going to be favored, so they are going to grow more in number, and you're going to have warming temperatures because now you are trapping more energy from the sun by reduced albedo. Does this work? Well, there is some examples of cloud feedbacks, the emissions of cloud condensation nuclei favoring chemicals like dimethyl DMSP, dimethyl sulfate, and they create cloud condensation nuclei which would increase clouds and presumably increase albedo again, and so on and so forth. But overall, there is no evidence that life evolves to modify its environment. It's much more likely that life evolves to fit into an environment that exists, but there are lots of cooperations between different species which together can modulate the environment. But if you look at the satellite image of Earth, for example, here water vapor, clouds, dark surfaces, brighter deserts, darker vegetated regions, and so on, you know that there is a strong relation between rainfall, vegetation, albedo of the surface, water vapor, clouds, and so on. And of course, high altitudes, high latitudes obviously have snow and reflectivity and so on, which is involved overall in the energy budget, as we saw, where lower latitudes really receive more energy per unit area because it's a sphere. The curvature makes for a larger area receiving the same amount of energy. So you have energy deficit at higher latitudes when you include the outgoing long wave radiation, and you have excess energy being net excess energy in the tropics. That's what gives us weather and climate and so on. So it is tempting to assume that when you put all together, that maybe there is some kind of homeostasis happening. Leaving that aside and remembering that vegetation itself is also involved in the carbon cycle, we will come back to carbon cycle to see if carbon cycle also has something like a CO2 thermostat. That's the main idea of looking at geologic time scale stable carbon cycle. Okay.